Hello, Math 120, and this is Professor Gonzalez, and I'd like to go over some problems from Homework Assignment 2.6. Now, 2.6 takes a look at absolute value equations and inequalities, and it's the inequalities that can be a little bit challenging at times. But let's go ahead and get started. And I will pop in and out of a couple pages to do my own little take on maybe like a little lecture on this as we're doing problems. First one says, solve the absolute value equation. Of course, when you're looking at something like this, you may realize that when you take the absolute value of an integer, let's say 3, the answer is going to be 3. And take the absolute value of a negative 4, and the absolute value of negative 4 is 4. And so people kind of get the idea that all you have to do is just erase the negative, and then when you start getting into things like x minus 4, absolute value x minus 4, people think you could just erase the negative and put a plus, and then now it doesn't work anymore. So there's something more to it than just erasing the negative, right? So let's see if we can do a little bit more here. But on this simple problem, it says absolute value of x equals 2. So what could I put in for x? Well, the absolute value of negative 2 equals 2, and the absolute value of positive 2 equals 2. So you start getting the situation where you get more than one answer because of those absolute value bars. So that becomes something that you have to be aware of. So I think what I'm going to do is I'm going to talk a little bit about that with a visual. And let's call this absolute value equations. So we've got the algebraic definition of absolute value, which is great. I think right now I'm going to take a look at the geometric, which takes a look at a distance. It talks about this absolute value as being a distance, and we know that distances are always positive. So that kind of gives you a clue that how absolute values work. And so if we were to take a look at something like, let's say, a number line. Now the thing that causes confusion is a number line has positive and negatives, right? But 1, 2, 3. And let's say negative 1, 2, 3. So what this says, that wasn't supposed to happen. What this says, when you see this symbol, is absolute value. But it means, one definition says, it means a distance a number is from 0. So if we're thinking of it in that way, the definition of an absolute value is a distance a number is from 0. If we have the absolute value of x, we're saying what numbers or number have a distance equal to 3 from 0. So what this is saying is I'm looking for the number or numbers that have a distance that is equal from 3. So this is exactly 3 units from 0, and what number is it? 3. So one answer would be x equals 3. But when you look in the other direction, now we're talking about a distance, so this distance is still a distance of 3. And if I go the other direction, a distance away from 0 is 3 units still, but that location is negative 3. So that gives us our second answer. 3 and negative 3 have an absolute value of 3. And by the way, with these kind of problems with the equation, the proper word in between would be or. So that's one way to think about it. An absolute value of a number is just the distance the number is from 0. And so when we're saying the absolute value of question mark x, we're saying what numbers have a distance of 3 from 0? What numbers have a distance equal to 3 from 0? Okay, another thing to take a look at. So this works great when the number is positive. But here's another technique I picked up from actually a senior math instructor who retired quite a few years ago. But when you have an absolute value of x and it's equal to a negative number, let's say -3, if you can be aware, if you can be on top of it and realize that, hey, whenever there's absolute value and a negative, I want to be extremely careful because something strange could happen. Now, what's the clue for that? Well, the clue is absolute values is the distance a number is from 0, and you cannot have a negative distance. So if you think of it that way, you already have problems, right? So another way to think about this, though, is to say, at the end of the day, it doesn't matter how complicated the expression is inside the absolute value bars. At the end of the day, what is possible? Well, it's possible that the answer inside the absolute value bars, and then you take its absolute value, at the end of the day, it could be 0, or at the end of the day, after you take the absolute value of this, it could be positive. So it could be 0 or it could be positive. When is a 0 or positive going to equal a negative number? And that is never going to happen. So this would be no solution. So that kind of gives you a way of tackling those problems. When you see a negative, when you see an absolute value of a variable and it's equal to a negative, that's going to be a no solution problem. You could kind of even do this just to verify it, especially when you're still just learning it. No solution can be written as the empty set. It could also be written as the null set. Okay, we are going to come back to this page of notes after we do some more problems on the first page. So here we are on the next problem, and it says fill in the blank. We have this absolute value equation right here. The absolute value equation right here. And what I want to do is I want to write this. Let me just write it down again. Absolute value of 2x plus 4 equals 6. Now, if I was going to try to solve for x and moving things around, it's not going to work with the absolute value. We need to simplify the absolute value, get rid of the absolute value bars legally. And the way you do that is you realize that there is a positive case and then there's a negative case. And the positive case just basically says, if I could figure out what 2x plus 4 is, if that equals 6, that's going to give me an answer, right? And the negative case says, if I could figure out what 2x plus 4 equals -6, if I could figure out what makes that equal to -6, that's going to give me an answer, because ultimately, what's going to work in there? Well, a positive 6, absolute value of positive 6 is going to give me 6. But inside here also, the absolute value of -6 is also going to give me 6. So that's why we want to set it equal to 6, and that'll give me an answer. I want to set it equal to -6, and that will also give me an answer. So that's all they're asking right now. How do you rewrite an absolute value equations without the absolute value bars legally, right? That'll still give you the right answer. And that's how you do it, bringing it down to these positive and negative cases. So they're saying this highlighted absolute value equation is equivalent to positive 2x plus 4 equals 6, or, and of course, let me highlight that, the word is or in between, or 2x plus 4 equals what? The negative case, -6. So there's how that one goes. Let's see, what's next here is number 3, and number 3 says, solve the following equation. So let me see, did I have space for this on this page? Yes, I did have space. I used up the space there. Okay, I think I can squeeze this in if I get a little bit, if I zoom in maybe. So let's take a step on this first. Now, before we actually translate this into its equivalent like we did in the last problem, we took this problem with the absolute values and we rewrote it into its two equivalent positive and negative equations, right? Before you do that, what you need to do is you need to always isolate the absolute value. That just means, let me get a bigger pen here. That just means that you want to get this isolated. That means just absolute value on one side of the equation. And what do I have here? I've got a 5. I got to subtract 5 on both sides. So when I do that, that gives me the absolute value of 3x minus 4, and then I subtract 5 on both sides equals 5. Now what I want to do is I want to break this down into a positive and negative case, right? So the positive case, just says, whoops, just erased on me. The positive case just says that 3x minus 4 equals 5. And then the negative case just says, whoops, let me go back to that positive case. 3x minus 4 equals 5. I think I erased it when I hit backspace. And the negative case says that 3x minus 4 equals negative 5. And so we always want to have the positive and the negative, and this is after you isolate the absolute value. Notice we only have the absolute value on the left side of the equation, and then once we have that, then we can go ahead and write our positive and negative case. Now that we've written this down into equations without the absolute value bars, we can go ahead and solve by, of course, adding 4 to both sides, which gives us 3x equals 9. And if I divide by 3, I get 3, right? So x equals 3 is one solution. And then over here, I add 4 to both sides, which when I add 4 to both sides, I end up getting what did I do here? Okay. Let me finish that. I didn't mean to erase that much. 3x equals 9. Divide both sides by 3, and x equals 3. And then this one over here, we have negative 5 minus 4. That's going to give us a negative 1. So we've got 3x equals negative 1. Divide by 3. It's dividing by a positive, so you don't, well, there's not inequality. So anyways, scratch that. Now we divide by 3 on both sides, and we get x equals negative 1/3. And the connecting word between the two is or. So the answer is going to be x equals 3 or x equals negative 1/3. So we go ahead and put our answers in the solution here, and 3. Okay, I guess if I was going to circle the right one, it was what? The last one. I don't know why I'm doing this, because this is not actually a computer program. It's just a PDF of the computer program. Number 4. Number 4 says 2 times the absolute value of x plus 4 minus 3 equals 3. We want to isolate the absolute value. Once again, we want to isolate the absolute value. If we don't do that, we really can run into some trouble. We want to get this part by itself. So what I'm going to do is I'm going to add 3 to both sides. That's going to give me 2 times the absolute value of x plus 4 equals 6. I still want to get that absolute value by itself. I still have a multiply by 2 right here. So I'm going to divide by 2. And I'm going to write the result over here because of space. That gives me absolute value of x plus 4 equals 3. I don't like how, try to make this a little darker. So here's our absolute value equation. So notice what I did was I didn't solve for x yet because of the absolute values, but I did isolate the absolute value expression on one side, on the left side. Okay, so now that I've got this set, I'm all ready to do the positive negative case, right? So the positive, oh man, this thing. I don't know if I lost anything in that. So the positive case would say, that x plus 4 equals positive 3. And the negative case would say that x plus 4 equals negative 3. Of course, subtracting 4 off of both sides, we get x equals negative 1. Of course, subtracting 4 off of both sides here, we get x equals negative 7, because a negative 3 and a negative 4 makes negative 7. Once again, what goes in between? What goes in between is this word So I do this without erasing too much. Goes in between is this word or. Okay, write down the solution set. Well, solution is -7 or -1. Now, since we just solved this problem, I want to take a moment to run a check. And checks in math are recommended, but if you're on a test and you're running out of time, you probably should do the problem first and then check later. The other thing is certain mathematical procedures, the check is required because there might be an extraneous solution that's in the future of this class, but in the future. And other times, you're not checking for extraneous solutions. You're checking that you didn't screw it up, right? Not that the math procedure has kind of a built-in inherent error that your math could be correct, but the procedure needs to be checked also. So, but that's kind of rare. That's very rare in math. But those are checking for extraneous solutions at times. But right now, a check is optional. But the reason why I want to do a check is because I think it can help with our insight on this. Like, the insight, I guess, would be, you mean to tell me -7 makes this problem true and -1 makes the problem true? Yeah, it does. So I think when you check it, sometimes when you check it, it helps us understand how that is happening. So I'm going to check that what happens when x is -7. So when we check, we always like to go to the original problem just so we make sure we didn't screw something up in the process. And the original problem says 2 times the absolute value of x plus 4 minus 3 equals 3. Okay. And then the other one was, we'd like to check what x equals -1. And so the other problem, as we check it, would be 2 times the absolute value of x plus 4 minus 3 equals 3. So now I want to see what happens when x is -7. What happens when x is -1? We're going to do these simultaneously, I think, so we kind of see what's going on. So now you do not want to apply the absolute value bar before doing the operation, right? That -7, you can't just erase the negative. So -7 plus 4 is -3. And over here, -1 plus 4 is +3. And so maybe you're going to start seeing what's happening here. Why did -7 work and also -1 work? Why did 2 answers work? Well, because the absolute value of -3 gives me 3. And the absolute value of +3 gives me the same answer of 3. And so we will get the same answer on the left. So let's see, 2 times 3 is 6, and 6 minus 3 is 3. And that is perfect because that's what I had on the right. And so same thing over here. 2 times 3 is 6, minus 3 gives me 3. And that's awesome because that's what I had on the right. Check. So yeah, 2 answers work, and you can see the absolute value is going to make more than one answer work. And by the way, you use the positive negative case to set it up right up here, right? You use the positive case. We use the positive case and the negative case to set them up. It doesn't mean it doesn't mean that your answers have to be positive or negative, right? It doesn't mean that, right? We got 2 negative answers, -7, -1. Okay, we're going to move on to the next problem. And this next problem, let's see if you see something weird about this problem. And I'm going to pull out my highlighter. It says determine whether the following statement is true or false. Oh, well, actually, we're not going to work it. We're just going to do true or false. Still, something is unusual, right? And you should be highlighting that right there. Because x, at the end of the day, so I'm going to do this again. At the end of the day, I don't care how complicated this expression is, and x is not very complicated by itself, but at the end of the day, when you take the absolute value of whatever that is, it could be 0 or it could be a positive number. That's it. So when is a 0 or positive equal to a negative number? And that's never going to happen. So the answer is, Is this, they're asking, is this true or false? And we're going to have to say that this is what? It's going to have to, oh, I'm sorry. Absolute value of x equals -9 has no real solution. Oh, I agree with that, right? Because I said that's never going to work. No solution. Right, so I'm going to say it's true. Now I got to pick out which one is true. True because the absolute value of any of a real number is always 1. Well, that's no. True because the absolute value of any real number is always non-negative. Yeah, non-negative means 0 or positive. So that's going to be C. Okay, then moving right along here to the next particular problem. It says the absolute value, number 6, absolute value of 6x plus 7 plus 6 equals 2. And remember we said, I know what I said. I wanted to move this, number 6, onto my extra sheet of paper that I made here because we just don't have a lot of space and it gets so crowded. So I'm going to do this. I'm going to write this down as 6, and this 6 says the absolute value of 6x plus 7 plus 6 equals 2. So remember what I was saying, before I do any of the positive negative case, I want to get all of this stuff right here by itself. And so I can do that pretty easily by subtracting 6 on both sides. So when I do that, I still have my absolute value of 6x plus 7 equals -4. So I have isolated that. So now I'm ready for business, except for the fact that you should be highlighting something. You should be highlighting that negative symbol right there, right? That negative symbol. An absolute value, I don't really care how complicated it is inside, but the absolute value of a variable expression equals to a negative is going to be no solution. Okay, remember we could also call it the empty set, braces without anything in it, or the null set. Let me write that down, empty. So this is no solution or the empty set. Let's go up at number 6 and mark that. The solution is the empty set. There we go. And remember, the way we can logically kind of get through that is to say, I don't really care how complicated that is. When I have a variable expression inside the absolute values, at the end of the day, when you finally take the absolute value after simplifying everything, it could be one of two things. It could be a 0 or it could be a positive. And we're saying it's going to be equal to a negative. So that's no way. No solution, right? You can't, nothing's going to make that happen. So there's no solution. So let's move on to our next problem, which is 7. And number 7, if we go back to number 7, this is something a little different here. So we got to be careful. When you first see this, you almost think, okay, this is going to have like a billion possibilities. It's going to be crazy, right? Because you have absolute value. It's really not that bad. It's still only going to have a positive negative case. Really what happens is we have to use a set of parentheses, and that's where the mistake happens. But let me write this again. It says whoops, what happened there? It says the absolute value of 4p plus 26 is going to be equal to the absolute value of 5p minus 8. So we still have so, if I want to be a little more logical about this, and, I don't know if I think this loses some students, but it does, it is a good explanation. But if I want to be logical about this, basically, when this stuff right here in red equals this stuff in red, I'm definitely going to get an answer, right? But when this stuff in red equals the opposite of this stuff in red, I also get an answer because of those absolute values. So you still have the positive and negative case going on there. So let's go ahead and break this down into an equivalent statement that I can actually solve, because when we have absolute value bars, it's really complicated to solve. You end up getting usually one correct answer and the other one wrong. So this is equivalent to 4p plus 26 equals the positive case. So I'm just going to take, now you don't really have to multiply by a positive 1 because it doesn't do anything. But I'm just doing that just to kind of show you the positive cases. I want to know when this is positive, so it's just going to be 5p minus 8. I want to know that the positive outcome of that whole expression. So now the negative case, this is the one where people mess up. It's going to be, okay, take your expression 4p plus 26. We want to know when that equals the negative of that expression. That expression is what? 5p minus 8. And so usually when people do this problem, they get this one right on the left, the positive case, because you didn't really have to do anything. All you do is copy it down, get rid of the bars, copy it down, and solve. And so I'm going to do that. I'm going to subtract 4p on both sides, which gives me 26 equals p minus 8. I'm going to add 8 to both sides, and I get p equals, come on, scroll. That's going to be what, 30, where am I at? 34. So I get p equals 34. What about over here? Well, we want to make sure that we distribute our negative sign. And if you want to think of it as -1, that's fine. But you got to make sure you distribute that negative sign. So I'm going to copy down 4p plus 26 equals, what's negative times 5p? A negative 5p. A lot of times students get that, but this is where they forget it. Negative times a negative 8 makes it a positive 8. That's where the big mistake usually happens. Okay, let's solve for p. I'm going to add 5p on both sides. This gives me 9p plus 26 equals 8. I'm going to subtract 26 on both sides. This gives me 9p equals negative 18. And then I'm going to divide by 9 on both sides. This gives me p equals negative 2. And remember, the proper word in between is or. So let's go up to number 7 and fill it out. Number 7, the solution is negative 2, 34. I just feel satisfied by filling the bubble. Number 8, how much space do I have? Ooh, I kind of went a little bit too aggressive on the sizing of that one, but this is number 8. And number 8 is a similar kind of problem where it says 10z plus 25 equals the absolute value of 4z plus 31. Maybe if I zoom in, I won't use so much space. So remember the positive case. The positive case just says, okay, we need 10z plus 25 equals 4z plus 31. And remember the negative case. Oops, that's not negative. Remember the negative case. The negative case just says take 10z plus 25, which is equal to the opposite of the expression 4z plus 31. Okay, let's do the positive case first right here. And I'm going to solve for z. So how about if I subtract 4z off of both sides? This gives me 6z plus 25 equals 31. I'm going to subtract 25 off of both sides. This gives me 6z equals, what is that, 6? And I divide by 6 on both sides, and z equals 1. Or, what's this answer going to be? Don't forget to distribute your negative. That's the first thing you should do. Negative 4z and a negative times a positive 31 is negative 31. Super important step. The most common place to screw it up. 4z, add 4z to both sides, which gives me 14z plus 25 equals negative 31. Subtract 25. Now I've got 14z equals, let me move that up, negative 56. And divide by 14. And z equals negative 4. So there's my answer. It is 1 or negative 4. So let's go up there. The answer is 1 or negative 4. Okay, now we have something different. We have something different. Look at that right there. We have a less than symbol. Everything now has been equals. Now we've got a less than symbol. I need to talk about this less than symbol. So let me go back to my page of notes on page number 2. So remember when we had absolute value equation, how we thought about the distance from 0 to whatever. Let's do an absolute value. Inequality. So an absolute value inequality would be when you have an absolute value, and I'm going to use some of the same numbers. Absolute value of x, let's say, is less than 3. So what's the difference between the last one? Well, the last one said, I'm looking for the number that is exactly 3 units away from 0, and if I have 0 here, if I stretch my tape measure to the right, I go there, I got 3. If I stretch my tape measure to the left, 3 units, I got a negative 3. So I got 2 answers, 3 and negative 3. Now this is saying, the way I would say this, and I think I'm just going to verbally say it. The way I'd say that is I'm looking, so let's look at our model. Remember, absolute value is talking about the distance. A number is from 1, 2, 3, from 0. So, get some color. What this is saying is, I'm looking for the numbers that are less than the distance from 0 to 3. So here's 0, and what's less than? So there's 0. That's exactly 3 units away from 0. I want it to be less than. So the distance is less than this to this point is going to be all this stuff here. Right now I'm equal, and then this stuff out here is greater than the distance. So we don't want that. We want it to be, we're looking for the values that are less than the distance from 0 to 3. And if I stretch my tape measure from 0 to 3, this is exactly equal, has a distance of 3. And I want to find the values that have a distance that's less than. So if I go from here to here, that's exactly 3 units away. If I continue out here, that's more than 3 units, so it's greater. Less than is all this stuff in here, and we got to stop there. So the language, it does make sense with the picture. And so my answer to this would be this guy right here, right? Since it's not equal to it, you can't have it closed. And there it is, and if we did the interval notation, -3 to 3, that would be an answer. That is the answer. But you know what? The thing about interval notation is we can't manipulate it. Like when we have 2x, we want to solve for x. You don't do that with. But if we wrote it as an inequality, then that's something we do know how to solve and manipulate. So how do you write that as a compound inequality? Well, the way you'd write that is you would say the set of all x's, I'm sorry, no, you wouldn't say that. You'd say x is greater than, notice, -3, and x is less than +3. So this actually is translated into this equivalent statement. And once you translate it to this equivalent statement, you can manipulate it and solve it and things like that. Another thing to remember, and this is the way I'd go right here. I definitely would change it to that inequality. But there's something else that people often will say when it's a less than symbol, they'll use the word and the and word gets kind of hidden in here. Listen to what I say. X is greater than -3 and x is less than 3. So you see the word and is built in there, but we don't actually write the word and. So I would prefer that you write it this way. I think it's probably the best way to go. But you could also write it as two separate inequalities, just to kind of maybe clarify if someone's thinking that. If I write, oops, man, this thing just keeps on going to what I don't want. So if I write this part of the inequality and I read it backwards, x is greater than -3, x is greater than -3, then we are forced to use our and word, which is also the same as using an intersection. And then if I read from the inside out, and x is less than 3, and x is less than 3. And that squeezes my answers in between those two. And so this format, so this works, and this really highlights the fact that, there's the and word. So when we're doing absolute values and we see a less than, it's going to be an and it's going to be this interval kind of thing, right? Okay. Yeah, and this notation is really nice because, as long as you have these two less than, as long as you have these two, as you read from left to right, less than symbols, then that's going to be the small number, and that's going to be the large number, and that's kind of that's the right format for this kind of, for this compound inequality. Let's see if we can go do some of these problems. Now remember what we're doing. We're doing absolute values with a less than symbol. And we can rewrite that with an and, but you can see what are they doing right here. They're rewriting it as a compound inequality with two inequalities, okay? So how does this work? Well, what you want to do is you're going to want to look and see what is inside the absolute value. That's important. Well, whatever's inside the absolute value, that goes in the middle of this compound inequality. Okay, and then remember that whenever, and so I can't help but do this, but when I see a less than with absolute value bars, my brain knows that less than is an and problem. That means that you're going to have, so look at 15 right there. You're going to have a negative 15 over here and a positive 15 over here, and it's going to be squeezed in between, right? Gee, that's not what I want to do. It's going to be squeezed in between, and all of these absolute value less thaners will always be these and problems that look like this. Now the final solution doesn't go from negative 15 to 15 because all of this stuff right here needs to be adjusted when you solve. But when you're setting it up, it does, right? So you'd say 2x plus 3 is in the middle, and on the left side of this, it's negative 15, and on the right side of this, it's positive 15. And then you solve to go from there. But this one, they just wanted you to set one up. That's all we had to do there. Number 10. Nope, past number 10. Number 10, we're going to go to a problem that is not so complicated yet, but it is complicated in the way that it does have that absolute value and an inequality, a less than symbol. So I think what I want to do, because I have space, is to work this down here. Let me rewrite this. This is the absolute value of x is less than or equal to 4. So I'm going to use my logic here. And by the way, a lot of times books will just say, if you see an absolute value with a less than, just write your compound inequality with an and, done. But I do like to explain it. Some people that are visual might, visualize this every time. Some people might just get used to writing the and for less than and or for greater than. We haven't gotten to ors yet, 8 greater thans, right? But let's go ahead and do this. Remember, the absolute value is describing numbers that have a distance from 0. So there's 0. Our number in question is 4, right? So we go out 1, 2, 3, 4. And if I go to left, 1, 2, 3, 4, I also have a number that has a distance of 4 from 0. But this problem is more specifically saying, I want to know, I'm looking for these x values that have a distance that's less than 4 from 0. Well, exactly from 0 to 4 is right there. That's exactly a distance of 4. But less than that distance, right? Greater than that distance is out here. We don't want that. Less than that distance is in here. That's what we're looking for. And if we go the other direction, because distance is not positive or negative, right? If you're standing, I don't know what, you're standing in Sacramento and you drive to Reno, you might call that -4, but you go to San Francisco, it's +4, but distances, you don't say -4, right? So everything is just a positive distance. So now, once again, I'm looking for the x values that has a distance less than or equal to 4. Well, the distance that's exactly 4 is right here. Greater than 4 away from 0 is out there. So less than 4 from 0 to 4 is all that stuff. So that helps us to understand what's going on, right? So anyhow, so that's how I see this. I would just write this. I'd rewrite this problem as x is greater than or equal to -4 and x is less than or equal to +4, right? You might wonder where that came from. Let me use a little bit of color. You can kind of see the pattern though probably, but let me just use some color to explain that. Remember, it's an and situation. And so if you had this stuff in blue, which would say x is greater than, I'm sorry, there's an equal sign, isn't it? So we have to do, there's an equal sign, so it's got to be a squared off bracket. So that would say x is greater than or equal to -4. And then the other problem, this is from yesterday's work, you remember this. How would we actually say this part of the inequality? That's saying that x is less than or equal to +4. And then what's the answer? Well, the answer is just going to be the intersection of them, right? Or you could use the word and. And then, so that's why it drops down. You end up dropping down to just the red because it's the and. Okay, all that is great and all, but you know, once you start believing this stuff, it's so quick just to rewrite it like this and then go. All right, so there's our answer. We're done. How do you write this inequality as a interval notation? The solution as interval notation goes from -4 to +4 and it's closed. Let's go and put that in. They want this one to be, there it is, interval notation. So -4 to +4 and it's closed. And then what graph looks like that? Well, it's going from -4. It's going from -4 to +4 and it's closed. Yeah, it's D. Next problem, number 11 out of how many? A billion? No, I think we're getting there. So once again, I'm seeing less than, right? Now this problem is made to just help you kind of step through the process the first time when it's getting a little more complicated. Remember, when I see the values inside the absolute value, that particular expression ends up follows me right there when I'm translating it into this compound inequality. Remember, it is less than, so it's going to be an and problem. And what do? Well, it's going to be 2x minus 1 is greater than -13, and 2x minus 1 is less than or equal to +13. And so you can always look right there. As long as you've isolated this, right, got the absolute value on the left side, then you just grab that constant on the right and -13 and +13, as long as your your inequalities are facing in the less than position. Okay, so that's our first step. The next step, they're giving us, little steps, just stepping this along. It says, well, how about if you add 1 to all 3 parts? Okay. Oh, they did that. It's a little confusing here because, look at, they added 1 here, they added 1 there, they added to all 3 parts. And when you do that, you get -12 there. Of course, that zeroes out, giving us 2x, and that becomes 14. Then the next step, they say, well, what about dividing all 3 parts by 2? So they're doing that. What does that result as? Well, -12 divided by 2 is -6. 2x divided by 2 gives us just x. 4 divided by 2 is 7, and we got ourselves an answer. Done. Okay, they'd like us to write this in set builder notation. Okay, and that's fine and everything. You might want to graph it first. Sometimes graphing helps us to see the set builder notation. I'm going to graph a 0. Critical value is -6 right here, and then 7 is the positive side. There doesn't have to be a positive negative side, by the way. There is when you're setting up, but the final solution doesn't have to be positive and negative. Let's see, this says, shade the x values that are greater than -6. Well, that's to the right. That's to the right. And at the same time, x must be less than or equal to 7. So you can't go past 7. Now, when you see an equal sign there, that means we're going to have to close. It means -6 is part of the solution. And I see equal signs there, which means 7 is part of the solution, so we have to close it off. And so there is the solution in interval notation. Write the solution in set builder, no problem, it's right there in front of us. -6, so it's going to be x is greater than or equal to -6 and x is less than or equal to 7. Interval notation, this goes from a closed -6 to 7, and it's a closed interval. What else? Oh, find the proper, the correct graph. Well, provided that that's -6, let's see, -1, 2, 3, 4, 5, -6, and 1, 2, 3, 4, 5, 6, 7. That's got to be it. It's closed, -6 and 7. And we go to the next problem. Number 12, solve the following inequality. Okay. I think I've got space down here. Let's do number, well, that's not going to take too much space. Yeah, I should be able to fit this in here. I got space there too. Let's put 12 up here. This is number 12. And number 12 says absolute value of 2x minus 3 is less than or equal to 11. I guess I could have put up a little higher. So what we want to do, we want to make sure that the absolute value is isolated on the left side, and that we simplified all our constants on the right, so we're good there. Noticing that it's a less than, we know that that's going to make an and problem with these compound inequalities, right? So we have to do though is we have to put this pink stuff inside the absolute value bars in the middle, and then it's simple. You grab that number, and on one side it's negative, on the other side it's positive. So that's what we've got to do. So let's do it. So we grab this pink stuff, which is 2x minus 3. We say so 2x minus 3 must be greater than or equal to -11, and 2x minus 3 must be less or equal to +11, and that fits this format, which is an and. Now we need to solve, and we can do that easily, and we can also just remind ourselves that we've got 3 regions that need to be justified. Whatever we do the middle, we have to do the left and right. So we can see if we add 3 to the middle, we better do that to the right and better do that to the left. So what does that give us? It gives us 2x in the middle. 11 plus 3 is 12. Don't forget our inequalities. -11 plus 3 gives me -8. Don't forget our inequalities. So now we divide each of these pieces by what, 2? All 3 regions. And this gives us -8 divided by 2 is -4. And 2x divided by 2 is x. And 12 divided by 2 is 6. And we have ourselves a solution. And we're number 12? Let's see something. I think I made a mistake somewhere. Oh, there it is. I see it. Who caught it before me? Someone caught it early. Okay, the mistake is 11 plus 3 is not 12. 11 plus 3 is 14. Dang it. Maybe I said another word. Bad word. 11 plus 3 is 14, and 14 divided by 2 is not 6. It's now, what, 7. Okay, so now I've got the answer. This is basically saying all the numbers that are greater than -4 or equal to 4 and less than or equal to 7 will make this inequality true. Okay? All right, let's find the answer. Okay, so we've got our x in the middle, and we have less than, right? So, well, this is going to be easy. It's just going to be x is greater than or equal to -4. Notice I'm reading it from the inside out. And x is less than or equal to 7. So that's done. Next problem, write this in interval notation. Well, it goes, because of these equal signs, it means it includes the endpoints. So this just goes from -4 up to 7, and it's closed. And that should help me find my graph, being that it goes from -4 to 7 is closed. It's got to be D. So then we take a look at number 13. It says fill in the blanks. The absolute value inequality of absolute value 5x minus 1 is greater than or equal to 8. Okay, we got a game changer here. Now we have not less than, we've got greater than. This is something different we haven't seen yet. That's something different. Now, greater than symbols with absolute values is going to produce an OR, so you want to try to remember that. OR, greater than is going to OR, and you can see it right here. So if I want to rewrite this in an equivalent way that I could actually now manipulate by using algebra, I need to go back to my notes. Because back in my notes, I covered an absolute value of a variable x is equal to a positive number. Then we covered an absolute value of x is less than a positive number. Now we need to cover the absolute value this is absolute value inequality also. And this one is now going to be an OR because it's greater than. So you could have that memorized and not understand what's going on and still get them right. That's kind of dangerous math. A lot of times that does happen in math because of time and people just need to get through. But I'm going to try to explain it to you. Now that explanation is good one time or two times, and then after that, you don't need to draw every little thing, but unless it helps. So last time it was less than. So we're going to do this. Absolute value of x is now greater than 3. So we go back to the idea of absolute value is a distance from 0. So if I want to know exactly the distance from 0, so this is the absolute value of 3 because it's exactly a distance of 3 units away from 0. But what does this problem want? This problem is looking for we're looking for the numbers that have a distance that's greater than. Well, when I go from here to here, it's equal to 3. And greater than is out here, right? We're talking about a distance, right? If I'm walking along in this direction and I say this is equal to 3, greater than 3 is out here, less than 3 is back here. Greater than 3 is out here. So when you're talking about an absolute value with a greater than symbol, it's pushing us out, away from 0. And also, we got to remember that because absolute value doesn't care that this is a -3, it only cares about the distance. Well, then when we're going this way, we go 0 to 3. The absolute value of -3 has a distance from 0 to 3. So this is a distance from 0. So this is a distance of 3. We're asking what numbers have a distance that's greater than 3. Well, this is less than 3, less than 3, less than 3, less than 3. I'm walking away from 0. Now I hit 3, and I've got a distance from 0 to 3 is 3. And I keep on walking. This distance is greater than the distance from 0 to 3. So greater than that distance is all this stuff out here. So something to remember is that when it's an AND problem, it's going to be this interval that's locked in, right? So that's an AND. It's less than the distance from those endpoints to 0. And this one is greater than this distance from 0 to whatever the endpoint is, like 3. And so this is not an interval. It's an open interval that goes out. These two rays that point out. And the way that we can write this, so if you believe this, if you look at this and you can see this, well, how would you describe that? Well, I'd describe that as saying x is less than -3. Or, I've got to describe this side now. This one is x is greater than 3. And so this is the equivalent of that statement, but it's a statement that we can now use our algebra to manipulate. Okay. If there was anything else I wanted to say with that, I think that's it for right now. Just as a quick review, absolute value of x is equal to 3. You have a positive and negative case. You're going to have a couple answers, unless you're trying to take absolute value of x is equal to a negative number or 0, because right, the distance from 0 is 0, so you're not going to have two answers there. And then the absolute value of x is less than a number. Well, that's going to be an AND problem and have that kind of picture, and it's going to have that kind of breakdown using a compound inequality with an AND. And then if its absolute value of x is greater than 3, it's going to be an OR problem, right? And you're going to have these two values, and it's going to be an OR, where it's a union, right? OR also means union. Okay, there's a union symbol. Okay, let's get on with our homework. Let's get this thing done and posted. If I can find where I'm at. 11, 12, 13. Wait. 13. We didn't do 13 yet. Okay, so 13, I just realized it's a greater than, and a greater than is going to be an OR problem. And so like we did before, we said, okay, so this stuff right here in pink goes right here. And it goes right here. If I was to show you a picture that uses 8 in it, it's not going to deal with the complexity of that pink 5x minus 1 expression, but it's good for setting up. Remember the picture I showed you with the OR problem, with the greater than problem? It had a positive value here, like 8. I'm using 8 because of that 8. It had a negative value there. And remember, these greater than, absolute value of greater than symbols are going to be these OR problems that have these rays that shoot out. And so that usually helps us graph, or helps us set up the graph. What is this supposed to say right here? It says 5x minus 1 is less than or equal to negative 8 to get that picture going. And then 5x minus 1 is greater than, this is greater than positive 8. So you have this positive 8 and negative 8 thing going on, right? The thing you got to be really careful, because before, when it was an equation, you said I want positive case, negative case, but you got to be very careful of the inequalities and the way they face. And so what you want to do is this negative, right? In order to have this ray go out to the left, well, you got to have that negative one, and you have to stay smaller than that. And then to make this ray go to the right, I got to have that positive one, I got to go bigger. So you see, I've got 5x minus 1 is less than or equal to negative 8, or 5x minus 1 is greater than positive 8. Okay. Let's see if we can break this one down. And do I want to do a picture on this one? Yeah, I think I do, since we're doing greater thans again. Okay, so number 14, we got some space right here. This says absolute value of x is greater than or equal to 9. So if I'm going to run through the logic here, there's 0, there's 9, there's negative 9. This is saying I'm looking for the x values that are greater than or equal to 9. Now, let me say this again. I'm looking for the x values that have a distance that's greater than or equal to 9. Distance is the absolute value piece. So right now I've got a distance from 0 of like 1, I'm at 4, I'm at 5, I'm at 6. My distance is 9. So that's exactly 9. But I want it to be greater than that. So I keep on walking, and this is the stuff we're supposed to be looking at, right? It has a distance that's greater than 9. It also wants to be equal, so I better put my little square bracket that includes 9. Okay, now this other way, okay, I'm starting at 0. I don't care that it's negative. I'm still walking down this path. And now how far am I from 0? I don't know, 4. Now I'm 5. Now I'm 6. Now I'm 7. Now I'm exactly 9 units away from 0 right there, right? I don't want to be exactly 9 units away from 0. I want to be greater than 9 units from 0. So this is the stuff I'm talking about, stuff that's greater than 9 units from 0. And so we're talking about that. And because of the equal sign, I got to include 9, negative 9 rather. So that's my answer. Okay, can you actually write that answer mathematically with inequalities? Yeah, you can. X, say the stuff in red that says x is less than or equal to negative 9. How do you say the stuff in green? X is greater than or equal to positive 9. And what goes in between? It's an OR problem. There's no overlap, right? It's an OR problem. And that's your answer. Okay, so let's go up and figure out what that looks like. It's not too far away. Well, you can see my drawing right here in red and green. Because of this equal signs, you know it's got to be a closed bracket. And that has, those are open. That only has one side to it. That's everything. That's okay. There it is right there. It goes from negative 9 down and positive 9 up, and it includes with the square bracket. That's my answer A. They also want us to write this answer in interval notation. In interval notation, it's a little bit wacky when you're talking about something that's not a perfect interval. But let's go ahead and show it right here, though. So the interval notation of this would be, okay, so this is going out to negative infinity, right? So negative infinity up to negative 9, and that's closed. This is an OR problem. We like to use union symbol when we're talking about when we're using interval notation. Then we start back up at 9 right here, and we go forever to positive infinity. There's the answer, and that should go right here. I don't know why I feel like I've got to write it again. Open, negative infinity, closed at negative 9, union, and then it starts back up at 9 and goes forever to positive infinity. And that finishes number 14. Let's move on to number 15. Number 15 is having us do one of these greater than symbol problems, which means OR. And they're stepping us through to try to help us out, kind of spoon feed us here on the first one. So this expression, what I'm telling you, what I keep on saying is when you're doing any of these problems with absolute value, first isolate the absolute value on the left-hand side and collect all your constants on the right side, because that can really cause issues. Now we've isolated, and what is inside the absolute value is this expression of negative 7x plus 1. Okay, and so that goes there, and that goes right here. Now, if you're thinking what I like to be thinking with these OR problems, when you see greater than, it's an OR problem, which means it's going to have this look of going this way and this way, greater than the distance. And when you see that little 3 there, you know that, oh, okay, that means that that's negative 3 and that's positive 3. Well, that's not my final answer because of all this stuff that's going to happen in pink, but our algebra can figure that out after we just set up a problem, right? So this problem is going to be, this pink stuff must be less than negative 3. And this pink stuff right here must be greater than positive 3. And there's my greater than symbol, and there's my less than symbol. Okay, the next step says, well, it says subtract 1 from both sides. Okay, well, that happened to be subtract 1 from both. Let's see, why? What's going on? Okay, so they just, last problem they showed us that little 1. Okay, this one they didn't show us. They just set it. So I'm going to show it right here then. So if I subtract 1 from the left side and 1 from the right side, that's going to give me a positive 2 there, right? Okay, and if I subtract 1 from the left side and 1 from the right side, that gives me a negative 4. And you can see that verifies with their next step. Then they're telling us we have to divide both sides by negative 7. And they're also saying, don't forget to reverse the inequality. Yeah, this makes this problem a little bit of a nightmare. Not too bad, but you know, having to reverse always is something that's easy to forget. So here we are, and we're going to divide, and man, this is really tiny. See if I can make my font smaller, and I can zoom in then. So now we need to isolate solve for x, so I divide both sides by negative 7. And I'm dividing, so notice what they did. We had to reverse our inequality. And a negative 4 divided by negative 7 is positive 4/7. And over here, we need to isolate for x, or to solve for x, to divide by negative 7. Once again, we're dividing by negative, so don't forget to reverse the inequality, and we get an answer, x is less than negative 2/7. Okay, now I think I can move out because I'll have a little more space to work. So now the next thing we want to do is write the solution in set builder notation. All we have to do is pretty much just copy it down. It's just going to be, the only thing is just, it doesn't matter which side you put it on, just as long as it matches up. They have the less than symbol right there, so I've got to, whoops, I didn't want to do that. They've got the less than symbol right there, so I've got to match this guy with the less than symbol, right? So I do have to take that one, which just says x is less than negative 2/7. And then on the other hand, this has a greater than symbol, so that means I had to take this one with a greater than symbol. So then I can say x is greater than positive 4/7. Remember, greater than symbols with absolute values, use an or. Write the solution in interval notation. Yeah, it's always a pain to do this in interval notation. How about if we find our graph first? And it says x is less than negative 2/7. Wait, what's the scale? 1, 2, 3, 4, 5, 6. Okay, so this is negative 2/7 there. And this is positive 4/7 there. That one's looking good. And notice that both of these symbols neither one of them has an equal sign. So we are not going to have any brackets. So that doesn't work. That doesn't work. Yeah, okay, it's B. Oh, and write the interval notation. Well, when you're looking at the picture, that does help, right? Because the interval notation, it goes from negative infinity all the way up to whatever that is. What was it? Negative 2/7 union. Then it opens back up right here, and they told us that was 4/7, or we figured that out, and it goes to positive infinity. So that's a little bit of pain with fractions and negatives and everything. I don't think I'm going to write that again in that little space. I think that's good enough right there. It goes from negative infinity to negative 2/7, and it's open. Union, and that goes from 4/7 to positive infinity, and that's open. So let's get back down to normal size and go to the next problem. So how much space do I have to work? Good, I could write it down here. So this is number 16, and I'm going to write it down here, and then go back and, so I've got space to work. Absolute value of x plus 3 is greater than 1. Okay, so the clues here is that I've got an absolute value, and I've got a greater than symbol. So my picture is, in my mental picture before we actually do the algebra, is a -1 there, a +1 there, and this kind of thing. Because I know it's greater than the distance. It's going to have that look to it. That's not my final answer. It's just a guide to help me. So what is true here, which is good, what is true is that this is already isolated, right? The absolute value is already isolated. So this little pink stuff, right? We rewrite that pink stuff, x plus 3, the expression in the absolute value, and then say that. How do you say that? That is less than -1. Then you take that pink stuff again, and write it over here. By the way, what's that pink stuff? X plus 3, expression in the absolute value. And you use that for a guide. What does that say? It says greater than 1. Greater than 1. And of course, this is an OR problem. And now you have changed this nasty inequality absolute value into something without absolute values that you can actually solve. So now what do? We solve. Subtract 3 on both sides. And I get x is less than -4, or I subtract 3 on both sides. And I get x is greater than negative 2. And I got it done. So let's go up and fill in the blanks. So I've got to write x is less than x is less than negative 4. So I'll be writing that here, x is less than negative 4. Then I got to say the other side of it, right? X is greater than negative 2. So I can do or x is greater than negative 2. And that's taken care of, and that was A. And then it says, can you write this in interval notation? Right, interval notation. Yep, I can. So remember, this is x is less than negative 4, so that's going forever to the left. So that's just going to go from negative infinity up to negative 4, and that thing is open. Why is it open? Because it's not equal, it's just less than. And then or is kind of reserved for set builder. Union, we like to use union for interval notation. And this says x is greater than negative 2, so we're going to start open at negative 2, and that goes forever to positive infinity. So there it is, negative infinity to negative 4, open, union, negative 2 to positive infinity, and that's open. And that belongs right here. And then our graph is less than negative 4. It's open. Where's negative 4 that's open? Oh, here we go. 0, 1, 2, 3, negative 4, and that's open, going to the left. And then it says, or x is greater than negative 2. That's negative 2, and it's greater than, so it's going to the right. That's definitely our graph. Then we move on to number 17, and we're almost there. Whew. This absolute value of 8x plus 5 is greater than negative 3. And you can see, oh my gosh, okay, I got all this work to do. Look at all this crap they want me to do. But guess what? If you can just take a second and realize, wait a minute, we're comparing this to a negative. And absolute value is a distance. So let me use a little logic before I, spend too much time on this dang thing. I think I got some, yeah, okay. So let's write it right here. This is number whatever. So it's going to be the absolute value of 8x plus 5 is greater than negative 3. And once again, I see that, and that is a big red flag, in this case, a big star, meaning be careful, because we can figure this out probably really quick if we just use a little bit of logic. And here's the logic. I don't care how nasty that is inside the absolute value. At the end of the day, if we were to simplify that and someone told us what x was or whatever, at the end of the day, that can only be two things. It could either be a 0 or it could be a positive number. Can a 0 or a positive number be greater than a negative number? Actually, wait a minute. A 0 and a positive number, they're always greater than a negative number. That's always. That's going to be always true. So that means all reals is what that means, right? All reals are going to work in this problem. So let's go up here and answer the question. And there it is, part C. On that problem, the solution set is x is the set of all x's such that x is any real number. Well, how do we write interval notation when we're doing all reals? Well, it goes from negative infinity to positive infinity. And how do we show all reals on a number line? We just shade the whole dang thing. There it is. Okay, I'm down to my last problem here, number 18, and I'm excited. So are you. So this says, find the absolute value of 4x minus 1 is greater than or equal to 11. So remember, this is a greater than symbol. Okay, greater than symbol has what kind of look to it? It's an or problem. Do I have space right there? I'm going to rewrite down here and work the problem. So the problem is absolute value of 4x minus 1 is greater than or equal to 11. Now what's been done for us is the absolute value is isolated. Awesome. And all the constant values are on the right-hand side. Good. I can see that this is greater than, so that's an OR problem. And I also know visually that this isn't the answer, but it's going to have this look to it, at least when I start the problem. It's going to have this look to it because it's an OR and it's a greater than problem. It will definitely have this look to it as an answer. That's going to help me set this problem up, because now I'm going to take this pink stuff inside the absolute value. I'm going to write some of it there, and I'm going to write some of it there. So this pink stuff was 4x minus 1 is, and now say that. What does that say? 4x minus 1 is less than negative 11. Or take some of that pink stuff, which is that expression 4x minus 1, and say that. What does that say? Well, that says the values are greater than 11. And now we're set up, and now we're ready to go. Now all we have to do is solve. So I'm going to add 1 to both sides, which is going to give me 4x is less than negative 11. Sorry, negative 10. Divide by 4, and we get x is less than. I divided by positive 4, so I don't reverse the symbol. And negative 10 divided by 4 will reduce down to negative 5 halves. I was sort of playing with this in the my math lab, and they'll take this as an improper fraction, or if you want to write that as a mixed number, that was going to work too. The next one, I add 1 to both sides. I get 4x is greater than 12. I divide by 4, and I get x is greater than, right? Divide by 4, I get x greater than 3, and this is an OR problem, okay? So we're looking good there. Let's go ahead and write in our answer. And, be careful. This stuff is so tiny, it's kind of annoying how small. Hopefully on your computer you can zoom in better. But there's a less than or equal to symbol. So that's, ooh, I lost my less than or equal to. See, there's the computer thing that kind of gives you a clue. I lost my less than or equals. Okay, so let me go back to that again. When I'm trying to fill this in, I see less than or equal to, so I've got to go to the answer that has less than or equal to. That's this guy. So I'm going to take that answer and write it in. X is less than or equal to negative 5 halves. And then this problem right here happened to be a greater than or equal to symbol. So yeah, there's my answer with a greater than or equal. So I take that and type it in or write it in. X is greater than or equal to 3. Okay, and so that was part A. Done, done, done. Oh, write the interval notation. Dang, okay. Well, the interval notation of this, so this part says, shade the x's that are less than or equal to negative 5 halves. So so this is going forever to the left, so that's negative infinity up to negative 5 halves. This actually probably is easier to do when we're looking at a graph. This one says shade the x's that are greater than or equal to 3. Well, greater than or equal to 3, there's 3, right? So you're going to start at 3, equal to it, so it's got to be closed. Goes to positive infinity out here. So that's what that looks like in interval notation. Negative 5 halves, and it's closed union, goes from 3 to infinity. Last but not least, graph it. And when you graph numbers, when you're graphing improper fractions like this guy right here, they can be really annoying to graph improper fractions. So what you might want to do is just change that to a mixed number. 2 goes into 5 2 times with 1 left over. So negative 5 halves is the same thing as negative 2.5. And that just makes it easier to look at your graph. Like for instance, this graph right here is saying negative 2.5. So that's looking pretty good right there. Other than the fact that this is closed and this is open, so that's not going to work. This one, that's my new favorite one. This says negative 2.5, so that's looking good and going to the left forever. And then I need it to be positive 3 closed, yep, and going to the right. This is it. D is the answer. And I think we've done it. We have finished a bunch of problems, and this solving absolute value inequalities and equations, especially the inequalities, really is a tough section for many students. So if you're struggling, you got to keep at it because it's definitely tough. Okay, I hope that helped out, and you take care. Have a good one. Bye.